Hey, welcome back. This is the review for the final exam. And the way it's going to work is I'll basically take like about one question from almost every section. There's 38 sections. I'm not going to include all the sections, but probably like one question. And then all you have to do is kind of make sure you can handle that kind of question and any variation on that question. So, for example, let's take a look at 11.1. 11.1, we're finally firstly introduced to vectors, and 11.1, and problem 13 is a good type of problem. You should be able to do any of these problems, but I'm just going to focus in on 13. So you should be able to do 13, you should be able to do 14, and any, if I want to hit like a variation on those problems, you should be able to do those as well. So for example, if I hit similar question, how they have those practice in other versions, you should be able to do the other versions as well. Okay, so it should be pretty straightforward. As long as you can master these types of problems that I'm doing in this review, you'll be fine. Okay. Okay. So f of x is negative 3x squared plus 5. They're giving us a point. I'll call it P at 1 comma 2. They want you to figure out a unit vector parallel to the graph at the given point. So first part A, I'm going to need the derivative because the derivative represents a tangent to the slope of the tangent to the curve. So in that case, it would be negative 6x, and then I'm going to evaluate it at that point, 1, 2. So plug in 1, I get negative 6. And that's basically you think of it as a slope of the tangent to the curve at that point. So you may want to rewrite it as negative 6 over 1. So go down 1, right, go down 6, right 1. Okay, so when you do your tangent vector, and I'll just write a vector first, and then I need the unit tangent vector. To just get the vector, you kind of think of this thing as slope. So y over x. So the x coordinate goes first, and then the y coordinate goes next. Okay. I need a unit vector, so I have to get the magnitude of this critter. So that would be the square root of 1 plus 36, which is 37. So my unit tangent vector is basically 1 over root 37, comma, negative 6 over root 37. Okay, part B, find the unit vector normal to the graph of f of x at the given point. So to get the normal vector, it's basically negative reciprocals, right? So if the original vector was basically negative 6, 1, the new one's going to be the negative reciprocal of that, or 1, 6. But you need a unit normal vector, so you're just going to borrow this vector and swap the coordinates and make one of them negative. Okay, so there's two possible answers. I'll just go with the 6 over root 37, comma, 1 over root 37. Okay, so you swap the coordinates and make one of them opposite. Okay, so you should be able to handle those types. So let's look at 11.2. Okay, so just determining if vectors are parallel. Problems like, so 11.2, number 10, and I guess number 11 in there. Yeah, 10 and 11, determine which vectors are parallel to the given vector. So we have z equals 3 to negative 7, and we get some choices, negative 6, negative 4, 14, 2, 4 thirds, negative 14 thirds, 6, 4, 14, 1, negative 4, 2, and then E, none. Okay, so what's the deal with this one? If you recall that the way these worked, a vector z is parallel to vector u when the vector u is some constant multiple, some scalar multiple of u. Okay, so when z is equal to some scalar multiple of u. So if you look through here, that first one, works, right? So it works, and you can even identify the scalar the scalar multiple. In this case, it would have been -2. So C is -2. The second one works as well. In this case, C looks like it's 2/3. The third one won't work. If you try -2, it works for the first two components, but then not the third. Similarly, for the fourth one, if you try to multiply by 1/3 to get the 1, and then the next one should be 2/3, so that won't work. And then, of course, there's 2 that work, so none doesn't work either. So your answers would be A and B. Okay. Getting into 11.3, you'll have to know the projection formulas. So 11.3. So if you remember, I'll kind of rederive it for you. What we're looking for is a projection of some vector u onto some other vector v. And to kind of accomplish this, what we want to do is resize the v vector into a unit normal vector and then give it a size that is the length of this side of a right triangle here. Okay, so typically they call this vector that we're trying to create W1, and then there's an orthogonal component, W2. I'll ask you to be able to find both of those, and you have to have the formula memorized. Okay, so to get the formula, then, like I said, what we do kind of first for the projection of u onto v, I resize the v vector into a unit vector. So that's v all over the magnitude of v. And then I'm going to multiply by the length of W1. And if you think of this right triangle here, you could say, well, cosine of theta is going to be equal to the length of W1, which is I want to make my kind of coefficient on this unit vector, divided by the length of u. Okay, and you could solve for W1. That doesn't quite give you the formula though, right? The formula, to get the formula, you're going to have to rewrite the cosine theta part. And so if you remember, cosine theta is actually equal to, if you have from our formula, it's a way of rewriting a dot product. Remember, so we had this formula, u dot v all over the magnitude of u times the magnitude of v. Okay. So cosine of theta is basically this whole thing, and then if you multiply it by the magnitude of u, the magnitude of W1 will just be equal to u dot v all over the magnitude of v. Okay. And that's the constant we need to multiply the unit vector by. So however you remember it, I always just derive it from that little triangle, and then I have my formula. Okay, so the book will give it as u dot v all over the magnitude of v squared as the coefficient on the vector v. All right, so anyways, 11.3, you're looking at problems like number 7, 8, 9. I'm not going to throw any physics problems on there for you. Maybe I should be labeling which problems I'm doing here. So I'm sorry, I'll do that. Excuse me. So 11.1, I'm thinking like something like 12 or 13 there. I mean, you're in Calc 3, you should be able to kind of find similar problems, right? You can do that. 13 or 14. 11.2. I'm thinking problems like, I mean, we just do so much. It's very difficult to kind of zoom in on what's important, what's not, I guess. But 10, 11. If you want a more challenging exam, I can definitely whip that up. But you don't know if you want that. So, anyways, 11.3, I'm thinking of problems like 7, 8, 9. So problems 7 to 9. And let's look at, I guess, number 9. That's actually a space vector. So we're given u as ijk negative 9, negative 2, negative 4. And then our v vector is going to be 0, 4, 4. So part A, they want the projection of u onto v. So in that case, I'll call it W1. That'll equal u dot v. So doing the dot product, you get negative 8 plus negative 16, which is negative 24, all over the square of the magnitude of v. So that's just without the square root. 16 plus 16 is 32. And then times the vector 0, 4, 4. Let's reduce this a little bit. So I get negative 3/4 times 0, 4, 4. And multiplying by the scalar, I'll have 0, negative 3, negative 3. Okay. To get the other component, W2, note from my original picture here, W1 plus W2 equals U. Okay. So part B, they want that orthogonal vector there. And I note W2 plus W1 is going to equal V, just from the way we add vectors. Right. So, or actually it's U, it equals U. So to find W2, I just subtract W1 over, and I have U minus W1. These should all be vectors. And so I'll have negative 9, negative 2, negative 4, minus 0, negative 3, negative 3. And of course that will be negative 9, 1, negative 1. Okay, so you gotta have that formula memorized. You have to be able to find these unit vector, the projections, and the orthogonal part of the projection. Okay, is that what they're calling it? What the heck do they call it? Orthogonal component of the vector component of u orthogonal to v. Okay, that's the other part of it. Sorry. Let's move on to 11.4. So 11.4, we're dealing with cross products. I was particularly interested in the area of parallelograms because we later use that when we're doing surface area and surface integrals, because you need to kind of add up all of those little surface areas, and that would give you the surface area of the surface. So I would be interested in problems, and they're not too many. I think there's only one of them here, so you kind of know what you're up against. Number 4, of course I won't give you that, I'll give you a variation on it. But anyways, 11.4, something like number 4. Be able to do that. So I'll give you two vectors, and you have to find the area of the parallelogram that is the parallelogram with these vectors as adjacent sides. So the one given here is 1, 1, 1, and then the v vector 0, 1, 1. And of course, to get the area, you just need the magnitude of the cross product. So you need to be able to take a cross product, however you do it. Cover up the first column, you get 1 minus 1, which is 0. Then negative. Cover the second column, 1 minus 0 is 1. And then the third column, cover that up, it'll be 1 minus 0 is 1. So in this case, I'm getting 0, negative 1, 1. And so the magnitude then, which will be the area of the parallelogram with those vectors as adjacent sides, is the square root of 0 squared plus negative 1 squared plus 1 squared, which is 2. Okay, square root of 2 is the answer. Okay. All right, let's move on to 11.5-ish. 11.5, you need to be able to figure out how to do, well, we were doing parametric equations of lines, but you should be able to do that because we've been doing that with vectors in the last section with the line integrals. So I'll focus in on making planes. Given some information, you have to be able to figure out the equation of a plane. So number 7, 8, 9. So what am I looking at? 11.5, number 7 to whatever, 11, I guess. And it's usually pretty easy. You just have to figure out what the heck the normal vector is. You can imagine one of my students' professors said that imagine the president is calling you at midnight and he needs to know the equation of a tangent plane, and you have to have that formula kind of right on the tip of your tongue. But number 9 is kind of the prototypical version that I'm used to seeing. They give you 3 points and you have to find the equation of a plane, right? The equation of a plane that contains all 3 points. So this one's pretty typical, but I don't have to choose this one. I can choose any from 7 to 11. Let's make sure you can do those. Okay, so what I'm going to do is kind of call these, give these guys names, and then I'll find PQ and then PR, and then find the cross product, and that'll give me my normal vector to the plane. So PQ is going to be 6, 0, 5. PR is going to be -5, -1, 9. And then I need their cross product. And so my vector will be covering up the first column, 0 minus -5, so that's 5. Covering up the second column, you have 54 minus, and of course this is a negative, so it's 54 minus -25, so plus 25. And then cover up the third column, -6 minus 0, and of course that will be 5 comma negative 79 comma -6 for your normal vector. You could usually resize that thing, but because it has that idiotic 79 in there, there's not much I could do, so I'm just going to have to use it. I'm going to use that along with this first point. So if you remember the formula, if this vector is given as a comma b comma c, the formula will be a times x minus x sub 0 plus b times y minus y sub 0 plus c times z minus z sub 0 equals 0. So in our case, pretty easy because we have 0, 0, 0 as our point. So it'd just be 5x minus 79y minus 6z equals 0. Okay. Okay. 11.6 then was about quadrics. Is that what we call them? For some reason I always want to call them quadrics, but I believe they may be called quadrics. Let me look that up again just so I'm not misleading you guys. But you have to be able to identify them from the cross section, so expect to be able to draw the traces, and then of course I'll give you the list of all the different names, and you just have to pick the correct name based off of what you know about mathematics. So anyways, 11.6 quadric surfaces. Okay, sorry if I call them quadric surfaces in the lectures. I apologize. But anyways, 11.6. So you're looking at problems like 6 to 13, I guess. So problem 6 to 13. And I'll just look at problem 6. So I have 4x squared minus y squared minus z squared equals 1. So I'm going to look at the traces. Let z be 0. So in the xy plane, you'll have 4x squared minus y squared equals 1. And you can kind of plot that. Here's x, here's y. So the x is first, so the branches are on the x-axis. Let y equal 0, so you're in the xz plane. You get 4x squared minus z squared is 1. Same picture, except I have x and z as my axes. And then let x equal 0, so you're in the yz plane. And in that case, you're not getting anything helpful, right? It's just the truth is there's nothing there. So usually when there's nothing there, that means you have two pieces, and that's going to be your hyperboloid of two sheets, right? Hyperboloid of two sheets. Okay, and you can kind of see it if you go into 3 dimensions here. So you would have kind of an, how would that freaking work? Kind of the, so what is this? So here's your y, here's your z, here's your x. So in the xy, you would have something like this. And then the YZ, you kind of have something like this. So, yeah, you're ending up with these two kind of bowl-shaped things on either side. So it's hyperbola two sheets. Okay. So is that right? Number 6? I mean, am I going insane? That's correct, right? Where are you? Number 6. Yeah, there's space in between hyperboloid. Okay. Yeah, so make sure you could do those. 11.7, in particular, I'm worried about converting from cylindrical to rectangular and vice versa. I don't remember if that was a section with spherical coordinates. I know some other colleges enjoy doing spherical coordinates. It's I think for the stuff I had to do, I definitely focus in more on the polar, so I apologize if you were hoping to learn everything about spherical. But anyways, 11.7, I'm looking for the homework. I have 20 pages open and I can't find it. Okay, so it's in here somewhere. So 11.7, we're converting polar to rectangular and vice versa. So you should know your polar, I mean cylindrical is basically like polar, right? So you should be able to convert back and forth for any. Okay, so where does this start? It's like number 5 all the way up to, I guess number 11. No, number 12, number 13. Yeah, number 13. So what did I say, 5 to 13? Yeah. Okay, and if you're more ambitious, you can do the spherical stuff as well. I'm sure if you go into astronomy or like you're making satellites for a living, that's probably important. But I'm not going to focus in on that. Okay, so anyways, let's look at number 12. Okay, and they give us r equals 4 sine theta. They want us to convert this to rectangular coordinates and give them a little picture. So recall that x squared plus y squared is equal to r squared. So you could get everything from that one little picture. You know, you're drawing it like this. This point right here is r comma theta, but you can also think of it in terms of x and y, and then this is theta, and then this is an r distance. So from the Pythagorean theorem, x squared plus y squared is r squared. And then you could do like cosine theta is adjacent over hypotenuse. In other words, x is r cosine theta. And then sine theta, of course, is opposite over hypotenuse. In other words, y equals r sine theta. And then you had things like tan of theta equals y over x. But it's just this main picture. I feel like if you remember that picture, you can get all of those formulas. Okay. So anyways, right here then, I should be able to kind of replace the r squared part, right? So I'd have x squared plus y squared equals 16 sine squared theta. And then recall that y is equal to r sine theta, right? And in this case, r is 4 sine theta, so this would be 4 sine squared theta. In other words, I could rewrite 16 sine squared theta as 4 times y, right? And then you could move the 4y over, complete the square. So you get minus 4y and then plus 4 on both sides. You get x squared plus y minus 2 squared equals 4. So the trace of it in the xy plane is just a circle with radius 2, centered at 2 on the y-axis. Okay, so the trace in the xy plane would be like this. And then, of course, you're letting z vary, so it's going to be a cylinder of sorts. Right. All right. So that's 11.7. 11.8. Oh, there is no. If there is 11.8, I'm skipping it. All right. So on the next chapter, 12.1. We're working towards doing derivatives, and we had a lot of physics stuff. So acceleration is just the second derivative of the position vector. We want the normal vector, the standard unit normal vector, the unit tangent vector, and curvature is also, I think, at the end. Okay, so you're allowed to use the formula sheets that I gave you on the test. So you could use the formula sheet from test 3. There was a formula sheet for test 2 right here. I'm not going to be putting any of the acceleration components on the test, but I will probably put at least one curvature problem on the test. So you could have this formula sheet if you need it. But anyways, 12.1. They sort of work a lot with domain and just the basics of these guys, and then work towards limits, and then I think towards derivatives, right? So what do we have here? Representing curves. Here's some limit problems. There's only one limit problem. There's two limit problems. So either number 17 or 18 is what I'm going to put on the test, or some variation on that. So number 17, we have the limit as t goes to 0 of this vector, e to the 7t sine of 5t all over 5t e to the, and it's easy, right? You just evaluate the limit of the components. So e to the 7t, you just plug 0 in for t, you get 1. This other guy is a 0 over 0 form, so you're going to have to do L'Hopital's. You get 5 cosine 5t all over 5. And then the third component, that you just plug 0 in for t and you get 1 again. Then finally you can evaluate the middle component. Plugging in 0, you get 5 times 1 over 5, which is just 1. And we have our vector 1, 1, 1. Okay, so they worked with continuity. They worked with they started introducing you to finding vector valued equations for curves. So that would be like a line integral, the start of a line integral problem right here, and at number 22. But I think the idea was going towards derivatives. So anyways, let's look at 12.2. Let's see what they had there. I think 12.2. Yeah, so we have derivatives. So I presume everybody can take a derivative of a vector valued function. That's not a big deal. Integral, you may have forgotten that. So any integral problem like 12, 13, 14, 15, so 12 to 17, I guess. So for example, number 13 I'll look at. And the thing people always forget about in this one is that little constant. I mean, people forget about the constant of integration in Calc 1, but here in Calc 3, they forget that the constant of integration is actually a vector of integration, a vector constant kind of thing. Okay. So anyways, to integrate, you just integrate the components. So we'll have 4t to the 4th over 4 is t to the 4th. 8t squared over 2 is 4t squared. And then this thing is going to be negative 3 times t to the 3/2 times 2/3, which should be negative 2t to the 3/2, and then plus your integration constant, which you need a little vector symbol over top. Okay, so no big deal really, but let's move on to 12.4. We'll skip 12.3. Let's go to 12.4 then. So if I don't put it on the, my review, it's not going to be on the test. But 12.4, we get into the unit tangent vectors. Principles, sorry, I think I called it standard, but it's the principal unit normal vector and the unit tangent vector are what we're after. I'm not going to give you any of the space versions because remember those were quite exhaustive computationally. So what worst case scenario, I'll give you something like number 3, but you should be able to do like 1, 2, so 1 to 3. I wouldn't put 4 on there because it's a space vector. I'm not putting the acceleration stuff on there, but then you should be able to do stuff like what the heck is that one? Number 9 to 11, I guess. But anyways, let's look at number 3. So I want to find the principal's unit normal vector and evaluate it at 2. Given, so I want to find this thing, n of 2, given that r of t is equal to t comma 6 over t, and t is 2. Okay, so first I got to get the unit normal vector, so I need the derivative. And then I need the magnitude of the derivative. Let's get t squared plus 36 over t to the 4th. You can rewrite that as square root of t squared plus 36, or actually this would become, is it all? What the heck am I doing? No, that's right. Yeah, so I find a common denominator. This would become t to the 4th all over t to the 4th, but then the square root of t to the 4th would be t squared. Okay, there we go. So my unit tangent vector, you take the reciprocal of the magnitude of the derivative and multiply it by the derivative, and you end up with, in this case, it looks like you're getting, the derivative of t is not t, it's 1. That's what I screwed up. I was thinking about something else. All right, so I got t squared all over the square root of t to the 4th plus 36, comma, the t squares cancel out in the second one. You get negative 6 all over the square root of t to the 4th plus 36. And the trick to getting the principal unit normal vector was to kind of draw a picture of it and then just do the components, swap the components and make one of them negative. But to know which one you got to make negative, you got to look at the picture. The principal unit normal vector points to the inside of the curve. Okay. But anyways, evaluating at 2, I'll have 4 all over square root of 52, and then negative 6 all over square root of 52. I'm going to need a picture. So if I take this thing and get rid of the parameter, I'll have x is t, so therefore y is 6 over t, which is now x, so 6 over x. When t is 2, I'm looking at the point 2 comma 3. Okay, so 1 2 1 2 3. It's right here. This graph is like this. Okay, it's a rational function with an asymptote at 0 and at y equals 0, x equals 0. And then at this point, the unit tangent vector, you see it's going in this direction. So it's going positive and then negative. Okay. We want the unit normal vector to go in this direction. In other words, positive, positive. So our unit normal vector then at 2 will just be 6 over root 52, comma 4 over root 52, because both components have to be positive to get that particular direction here. Okay, so I would expect you to draw a picture in order to get that answer. All right, let's go back to the material then. So that was 12.4. 12.5, I guess curvature, was curvature in this section? I swear it was, but I think I left it off the final. I don't think I put it on the final. So I'm sure some of you are very, very bummed about that. So actually, you don't even really need this this sheet here, this formula sheet too. You probably won't even need it. But anyways, 12.5, I was kind of interested in some of these arc length problems because that arc length formula comes up to be important once you're dealing with line integrals, right? So 12.5, let's look at that, and then we'll go on to 13. 12.5. So yeah, that's where the curvature was, but I'm not going to beat you up over that. Basically comes down to just inputting into a formula. But anyways, the ones that I would be interested in would be these here in the beginning. I wouldn't expect you to graph it, but I would expect you to be able to calculate those 1 to 4. And in order to do that, you need the integral for arc length. And so if you remember from what we did with the line integrals, the arc length integral is basically the integral of the magnitude of r prime of t dt. Okay, so in our work here, then what will that look like? It'll look like the integral of the square root of x prime of t squared plus y prime of t squared, which you may remember from Calc 2 then. That's just your arc length formula. Okay, and then if you took the derivative of s with respect to t, or ds, you would get just the magnitude of r prime of t dt, and then when you go to your line integrals, you of course had f dot dr, so this would be the same as the integral of f dot seems like then it's this thing, so maybe I should be calling it s. I'm getting myself into trouble here. So it's f dot, what the heck was it? So I knew I had to use that thing. Well, this would have been the unit normal. It's this thing, right? That's kind of where you start with this integral. And if you look at that vector t, what is that vector t? Well, that's r prime of t all over the magnitude of r prime of t dt. And you kind of see that magnitude of r prime of t dt is up there with that ds part. But I don't know. Man, that ticks me off. So I don't remember off the top of my head. I'm sorry. I apologize for that. I feel like I should rewind, and if they only made it easier to make these recordings. Okay, but anyways, for this section, you need that formula there. The other stuff is escaping my brain for right now, but you need that arc length formula. So, for example, number 2. Figure out the length of this curve. So I have t cubed plus t squared from 0 to 1. Whoops, need a comma in there. Okay, so I need r prime. Basically, that will give me the x prime and the y prime. So this will be 3t squared and then 2t. Then I'm going to integrate the square root of the squares, the sum of the squares of those derivatives. So 9t to the 4th plus 4t squared dt from 0 to 1. And now it's just an integral. So you can factor out the t squared. The square root of t squared is just t. So you get t times the square root of 9t squared plus 4 dt. Then you could do a u sub if you want. Du is 18t dt. So dt is du over 18t. So the t will go away. You'll have a constant of 1/18. And then you're integrating u to the 1/2 du. So that's going to be 1/18. Back subbing 9t squared plus 4 to the 3/2 now times 2/3 evaluated. So that's going to be 1/27 times plugging in 1. You get 9 plus 4, which is 13 to the 3/2. and then minus plugging in 0, you get 4 to the 3/2, which is 8. Okay, and that should be your answer. Okay, let's move on to chapter 13 then. I think I'll skip 13.1 and 13.2. 13.2 then introduced us to limits, and that's where you were like comparing different directions to see if the limit existed. So I'll just hit 13.3 then, and here we're looking for partial derivatives, so you should be able to do any of these really, just 1 to 16 basically. So 13.3, 1 to 16, and gotta find my tab. Where am I? Okay, so these were chain rule problems, and the chain rule comes up a lot in the proofs. So we want to, oh sorry, I'm getting ahead of myself. We're still doing the partial derivatives. Okay, so you have to be able to find the mixed partials. 16 is a good problem. Z equals 18x e to the y minus 14y e to the negative x. First partial with respect to x is 18 e to the y plus 14y e to the negative x. Zxx is going to be then negative 14y e to the negative x. Zxy, which if you look on the right, when you write it in Leibniz notation, it's actually probably not, it's not in the same kind of order that you see. So to do the derivative first with respect to x, you put that first in the denominator, and then to do the derivative with respect to y, you put that on the other side. So it looks backwards when you write it in the Leibniz notation, but I don't bother with it for that reason. But anyways, I just thought you should know that in case you get in trouble in the future. Hopefully prevent you from getting in trouble in the future. But anyways, taking the derivative of z first with respect to x, then with respect to y, you get 18 e to the y plus 14 e to the negative x. Okay, and then we need the rest of these guys. So z with respect to y is going to be 18x e to the y minus 14 e to the negative x. Zyy is going to be 18x e to the y, and then zy first, then x will be 18 e to the y plus 14 e to the negative x. And those mixed partials being equal would be sort of a criteria for a function to have a potential, a vector field to have a potential function. If you remember, that came up in that section. So they're in general usually equal so long as we meet some criteria. Let's remind ourselves what those criteria were. So 13, I think it's like continuity of the first partials or something, but I don't remember off the top of my head. So 13.3. It's trying to prevent me from seeing it. The criteria, equality of mixed partials. So long as the mixed partials are continuous, then it works. Okay, so if they're not continuous, you're not going to have that. But okay, let's move on to 13.5 then. And 13.5 is where you have the chain rule, okay, which I think is kind of important because it can help you in a bind. And some of the formulas, when we derive them, use the chain rule to derive the formula. It seems like when we were doing tangent planes, the reasoning for why the tangent plane uses the gradient as kind of the normal vector was dependent on the chain rule and part of its proof. It seems like that was true. But anyways, 13.5, pretty much, I won't put any like the you know, when they're each variable is dependent on two variables. But something like 1 to 1 to 6-ish, you should be able to do any of that stuff. Anyways, I'll look at number 4. W equals cosine of x minus y. You have x equals t squared, and then y equals 65. So I need the I need the derivative of w with respect to t. And the way to pull this off is the chain rule. So first you would do the partial of w with respect to x times the derivative of x with respect to t, plus the partial of w with respect to y times the derivative of y with respect to t. Okay. Then we just plug stuff in. So the partial of w with respect to x is going to be negative sine of x minus y times 1 from the chain rule, and then times the derivative of x with respect to t, which is 2t. Then plus the partial of w with respect to y, which would be negative sine of x minus y times negative 1, so it ends up being plus sine of x minus y, and then times the derivative of y with respect to t, that's just 0. Moving the 2t up front, I get 2t sine, substituting back in terms of t to get everything in terms of t. X is t squared minus y is 65, and that would be your answer. 13.6 we get into then, the gradient section is right after that, and then also directional derivatives. So you have to think in 3 dimensions. You no longer have just basically one slope, right? Because you have to imagine yourself on the side of a mountaintop, and if you twirl yourself around in any direction, there's going to be a different slope, right? So we consider the directional derivative in 13.6. Of course, we have the partial derivatives, which just tell you basically the slope in the x direction, the slope in the y direction, but now we want the slope in any direction. So anyways, 13.6, finding directional derivatives. So you should be able to handle 1 all the way up to 4. So problems 1 to 4 basically. So number 4, we want the directional derivative on the surface e to the 8y sine x at the point P 0, 0, going in the direction of the point Q, which is at 2, 1. Okay, so the formula for Duff was going to be the gradient of f dotted with the directional vector, and the directional vector has to be a unit vector. Okay, so the directional vector, we'll get that first. PQ is going to be 2, 1, but it needs to be a unit vector. So I need to find the magnitude. It's going to be the square root of 4 plus 1 is 5, and so the unit vector is going to be the 2 over square root 5, comma 1 over square root 5, and then I need the gradient of f evaluated at 0, 0, of course, but we'll just get the gradient first. So the gradient of f is, first with respect to x, it'll be e to the 8y times cosine x. Then with respect to y, the derivative of e to the 8y is e to the 8y times 8. So you get 8 e to the 8y with the sine of x hanging out. And then the Duff formula, and we're evaluating it at 0, 0. Is going to be the gradient evaluated at 0, 0, which is just 1, 0, dotted with this unit vector, and that should just be 2 over root 5. Okay. All right. Then going on 13.7, we're in the tangent planes, and to get tangent planes, you basically need a gradient for your normal vector. Okay, and we kind of, I believe that's where you kind of prove that gradient becomes a normal vector using the chain rule. But let's hit 13.6 real quick and kind of just remind ourselves of that proof. Tangent planes and normal lines. I'm not going to worry about normal lines. I thought that was a bit silly. But anyways, yeah, here. So if you remember that proof, it has that chain rule type feel to it. It even says, then it follows from the chain rule that this happens. So we had to use a chain rule to develop this formula, and to note that the gradient is going to end up being your normal vector for your tangent plane, and then of course they give you the equation of the tangent plane. So anyways, that's 13.7, I think. Yeah, 13.7. So 13.7, you should be able to develop the equation of tangent planes to any surface I hand off to you. So I'm not going to worry about the normal lines, just the tangent planes. So if I pick a later problem, I'm not going to ask you for the normal line or whatever they want. So problems 1 to 7 we're looking at, and I'll do the last one, number 7. Okay, so all I'll do is part A. I'm not going to put part B on the test. So I want to find the equation of the tangent plane to the surface, x squared plus y squared plus z squared equals 14. So a sphere at the point 1, 3, 2. So I need the gradient of this thing. So you can consider this as a 3-variable function. That's what you're going to have to do. Squared plus y squared plus z squared minus 14 is 0. And then the gradient of g will be your normal vector. Okay. And later on, when we're dealing with, like, I think it comes up in Stokes' theorem, right? You're kind of using a normal vector based off the gradient. This is a normal vector, but it's a unit normal vector. They want the unit normal vector when they do that Stokes' theorem. But anyways, the bottom part kind of cancels out. Okay, I'll shut up. All right, so this is 2x, 2y, 2z. Okay. So for the tangent plane, you just basically have to put the point into the gradient, and you're going to get 2, 4, 6, and then use the point along with the gradient as the normal vector. So 2 times x minus 1 plus 4 times y minus 3 plus 6 times z minus 2 equals 0. Okay. It's no big deal. 13.8 then got us into relative extrema. I think then from there it went into maximizing and minimizing problems. So that formula sheet on test 3, you may want that. Let's look at 13.8. So 13.8, basically, is this 13.8? Yeah. Those first ones you're kind of just guessing based off the picture, and then these later ones you're actually finding the d value. So 4 all the way to 11. I won't include those boundary type problems, but any of those you should be able to do. Let's look at number 6. Just kind of remind you how this works. It's a lot like what you did in Calc 1. You're basically finding the two partial derivatives, setting them equal to 0. That point will be one of your relative max, a relative min, or a saddle point, and then you use that d value from the sheet to determine which it is. Okay, the d plus the one of the second partials. Okay, so 13.8, number 6. Can't see it. I have f of xy equals negative 3x squared minus 9y squared plus 3x minus 18y plus 5. Get your partials. Fx is negative 6x plus 3. Fy is going to be negative 18y minus 18. You might as well, all right, let's set them equal to 0. Negative 6x plus 3, so negative 6x equals negative 3, so x is 1/2. Here you get negative 18y equals 18 when you set it equal to 0, so y is negative 1. Then you need to investigate your d value. So for that, you need to get fxx, fyy, and then fxy. So fxx is going to be -6, fyy is going to be -18. So, and then fxy I need as well. Sorry, still need to get that. So fx then with respect to y is just 0, and then d will be fxx times fyy from your formula sheet. So it's going to be 6 times 18, which is 108, I think. And then minus fxy squared, which is 0 squared, which is 0. Ultimately, that's 108, so our d value is greater than 0, so it's either a max or a min. It's then dependent on your fxx value, and our fxx value is negative, and I kind of think of that as kind of a concave down situation, right? So you're going to have a maximum. So a max at the point 1/2 -1. Okay. If they want the max, then you just have to put that back in there. I'm good with that. I don't need you to put that into the function and evaluate it. That's a bit too much for me. But yeah, anyways, relative max at that point. So you're finding relative extrema. Then in 13.9, you're using this idea to minimize or maximize stuff. And then in 13.10, that was Lagrange, using Lagrange's theorem, I guess. So let's look at 13.9. And these are fairly simple. They just come down to doing a kind of a... So I'm not going to put 1 or 2 or those distance formulas on the test. I'm not putting those on there. It'll be like 4 or 5 or 6. Okay, so 13.9 for the 6. So look at number 5. They say the sum, there's 3 positive numbers, so none of them are equal to 0. The sum is 8, so that becomes your constraint formula. And then the formula you want to optimize is this product, xy squared z. Okay. All right. So the way it works is to first reduce the number of variables in the optimization formula with this constraint formula. Okay. So z is going to be equal to 8 minus x minus y. So I plug that into here and then get the partial derivatives, set each equal to 0, and find that point, and that will be your answer. Okay. So in this case, p then will equal 8xy squared minus x squared y squared minus xy cubed. So px is going to be 8y squared minus 2xy squared minus y cubed. Py is going to be 16xy minus 2x squared y minus 3xy squared. Set them equal to 0, factor them. I can factor a y squared out of the first one. So I get 8 minus 2x minus y. And then the second one I can factor out xy. So I'll have 16 minus 2x minus 3y. And you could throw out the y squared portion and just write 8 minus 2x minus y is 0. Basically, you're assuming y is not 0, so you could divide both sides by it. Likewise, on the other one, you can throw out the xy, so 16 minus 2x minus 3y. And then you could solve for y on the left here. Get y is 8 minus 2x. Substitute that into here. So 0 is 16 minus 2x minus 3 times y, which is 8 minus 2x. So you get 0 equals 16 minus 2x minus 24 plus 6x. And then that will be negative 8 plus 4x. So 4x equals 8. So x equals 2. Back subbing into the y formula, y equals 8 minus 4, which is 4, and then back subbing again into the z formula, z is 8 minus x minus y. So 8 minus x minus y is 2. That would be your answer, 222, or 242, sorry. Okay. Finally, then 1310 is the Lagrange stuff. So basically all you're doing there is taking the gradients and setting them equal to each other. You get the same answer. Whoops. I wish we were in 15.8 already. 1310 Lagrange stuff. Okay. Use Lagrange multipliers. All right. So anything like 1 all the way up to, I guess they're all pretty simple. 1 to 5. So 13.10, looking at 1 to 5. And so I'll look at number 3. We want to use Lagrange multipliers to maximize this fxyz thing, which is x squared plus y squared plus z squared, the sphere, on the constraint that x plus y plus z minus 12 is equal to 0. Okay. Okay. So you find consider the second function a function called g. And then we're going to get the gradients of each function. The gradient of f is 2x, 2y, 2z. And then the gradient of g is going to be 1, 1, 1. And then you set gradient of f equal to a constant multiple of the gradient of g. Okay. Kind of looks like, I don't know. All right, so equating components, then I get 2x equals lambda, 2y equals lambda, 2z equals lambda. So just multiplying, the gradient of g times lambda, you get lambda, lambda, lambda. If you've ever seen Revenge of the Nerds, I believe that was their fraternity. But anyways, you have that set of equations plus the constraint equation, and you use those to find your answer. Okay, so from these equations, I can see that x is equal to lambda over 2, and that will be the same for y and z. So I could place that expression into the constraint formula, and that will give me lambda over 2 plus lambda over 2 plus lambda over 2 minus 12 is 0. Solving for lambda, then I'll get 3 lambda over 2 equals 12. So lambda will equal 2/3 times 12, which will be 8. Okay, and then back summing that into this formula, you get that x is equal to 8 over 2, which is 4, which of course is equal to y, which is equal to z, and then that's your answer, 444. The actual value of the maximum then is just going to be f of 4, 4, 4 is going to equal 16 plus 16 plus 16 is 48. Okay. Finally, in the chapter now 14, integrals. Okay, so 14.1, you should be able to let's take a look. Thinking problems. Yeah, I mean, clearly you should be able to evaluate, but I'm more interested in, can you set them up? Can you switch order? So problems like, I don't know. You don't like the ones where they give you a picture. So 18 to probably like any of those. 18 to 20 something. 18 to 28. Is that too many for you? That will be good. You should be able to do any of those. 18 to 28. And I like the ones where you kind of have to sketch and then switch the order. So something like number 21 would be a good bet. So I have negative 4 to 4, and then the integral from 0 to the square root 16 minus x squared, f of xy, dy dx. So first sketch it. So y equals 0 to y equals square root of 16 minus x squared is that region. And then negative 4 to 4 on the x-axis will give you the whole half circle, that region. Changing the order of integration, then I have to integrate from basically x equals this curve, which is negative square root of 16 minus y squared, to this curve, which is positive square root 16 minus y squared. And then your Riemann man in this orientation, I broke his leg. He's going up in this direction like this, and he is going from 0 to 4 on the y-axis. Okay, and then don't forget your f of x, y, and then dx, dy, because we changed the order. Okay. So be able to do something like that. 14.2 is more of the same, just sketch and evaluate. I mean, I think we're good with 14.2. 14.3 is on converting to polar, so let's just skip 14.2. So 14.3. Problems like 3, well, that's just evaluating, right? Evaluate and sketch. So problems like 6 to whatever, 6 to, I wouldn't do anything crazy. How about 6 to 11? I'll try number 7. So here they want you to evaluate the integral by converting it into polar coordinates. I'm going from 0 to square root 64 minus x squared, and then negative 8 to 8, and we have x squared plus y squared dy dx, I guess. Okay. Actually, okay, this is fine. I'll do this one. Doesn't matter. That's I wrote the wrong problem in my notes, but it's fine. Okay, so on the y-axis, I'm going from y equals 0 to y equals square root 64 minus x squared. And the x-axis, I'm going from negative 8 to 8, so it is this semicircle here. So in polar coordinates, replacing x squared with y plus y squared with r squared, and then I have r dr d theta, so it would be r cubed dr d theta. And then I'm going from 0 to 8, the r value 0 to 8, and then I'm rotating from 0 to pi. Okay. So here I'd have r to the 4th over 4. Okay, so 8 to the 4th over 4. Then d theta. So it's just going to be 8 to the 4th over 4 times pi. And I assume that's 1024. Yeah, and then times pi. Okay. So that's 14.3. We do so much in this, and I complain about it every year, but nobody listens. Anyways, 14.5 then is, I believe it's surface area. The first time we see surface area. We see surface area later in the vector analysis chapter, and there there's two forms, a parametric form and then this form, z of f of xy. So 14.5, surface area. Let's just delay this until we get to the other surface area section, because there's two. It's kind of like there's two sections for surface area, and just move into 14.6. Okay, and 14.6 was then on finding integrals with triple integrals, or finding volume with triple integrals. Okay, just need to find a way to kind of cut down on the millions of sections that we are investigating here. Okay, so you should be able to do any triple integral, but I'd be more interested in actual applying these for volume. So like 6 all the way to 11, 6 to 11. And I'll look at number 9. So use triple integral to find the volume of this object. Z equals 6x squared, y equals 3 minus 3x in the first octant. So you have to set up your triple integral, and that may include having the graph a little bit. But anyways, we're integrating over that xy plane, that region of the xy plane in the first octant, and in the xy plane I have that line y equals 3 minus 3x. So it has a y-intercept at 3, and then the slope go down 3 over 1. So it's this region we're integrating over. So on the in the xyz space, I'm integrating over this region, and the object I'm integrating under, I guess, or trying to find the volume of, is kind of a parabola, a cylinder parabola, if you will. It's kind of like this thing. Okay, so trying to do my best to draw it, but I sort of lost my perspective and everything. I think it will be like this, right? Something like that, and then you're finding the area underneath it. Okay. Oh, yeah. Yeah, something like that. Okay, so anyways, our integral, I always go surface to surface, curve to curve, point to point. So surface to surface, 0 to 6x squared. Curve to curve is 0 to 3 minus 3x. And then point to point, 0 to 1 in the x. So dz, dy, dx. Evaluating, I'll have z, dy, dx. Substituting in 6x squared for z, you get 6x squared, dy, dx. Then integrate with respect to y, so you get 6x squared times y, and substituting in the limit there, 3 minus 3x. And then it's with respect to x, so it's going to be 18x squared minus 18x cubed from 0 to 1 eventually after I do dx. So that would be 6x cubed minus 9 halves x to the 4th from 0 to 1. And that would be 6 minus 9 halves, which will be 3 halves, right? 12, 9, yeah, 3 halves. Yeah, okay. Yeah, all right. 12, 7, and then what is that? 14, 7, 14, 8. Seems like we were doing Jacobians in 14, 8. I'm going to leave that out, and then 14, 7. Just doing triple integrals with cylindrical coordinates and spherical coordinates, so I'm going to leave that part out, and then skip into chapter 15 on vector analysis. Okay, I'm going to skip 15.1. 15.1 was kind of just, can you plot a vector field with a bunch of little arrows, and then telling if then we worked a little bit with curl and divergence, which we use ultimately for Stokes and the divergence theorem in 15.7 and 15.8. But so we'll start with 15.2, doing the line integrals in kind of the scalar form and the vector form. I'll zero in on the vector form for the final exam. So problems like 8 to 11, I guess. So in particular, the vector version. So we'll try number 10. So I want to find the line integral of the vector field on the curve C, f.dr. And the vector field is given as x squared, y squared, z squared. And then the curve is this thing, r of t equals 2 sine t, 2 cosine t, 1/2 t squared, and we want to integrate from 0 to pi. Okay. Right, so in this case, I need dr, right? So I need r prime of t, and then I need to parameterize everything in terms of t for my integral. So I'm going to have 2 cosine t, comma negative 2 sine t, comma t, and then my integral will be the dot product of f and r prime of t dt from 0 to the pi, reparameterizing f then in terms of t using r of t. I get 4 sine squared t, comma 4 cosine squared t, comma 1/4 t to the 4th, and then dotted with r prime, so that would be 2 cosine t, negative 2 sine t, and then t dt. This one's kind of obnoxious looking already. So I get 8 sine squared t cosine t minus 8 cosine squared t sine t plus 1/4 t to the 5th dt from 0 to pi. Unfortunately, you can't do any Pythagorean identities because there's a minus in there and you can't really factor anyways. So you're going to end up having to just do u subs. From the first one, it's a sine t u sub, and then you get your du is cosine t dt. So the first integral would be 8u cubed over 3. Back subbing, you would get 8 sine cubed t all over 3. The second integral, then you need a u sub on cosine, and then your differential would be negative sine t dt. So the sign will change. It'll be plus 8u cubed over 3, back subbing 8 cosine cubed t all over 3. And then finally, plus 1 24th t to the 6th. Evaluate from 0 to pi. Plugging in pi, sine of pi is 0. Cosine of pi is negative 1. Negative 1 cubed is negative 1, so you get negative 8/3 plus 1/24 pi to the 6th minus, plugging in 0 for sine, you get 0. Plugging in 0 for cosine, you get 1, so you get 8/3 here. And then plus 0. So it's going to be negative 16/3 plus 1/24 pi to the 6th. Okay. All right, so 15.2 is there. 15.3 then was on the sort of fundamental theorem of line integrals and conservative properties of line integrals. So basically, if you know vector field is conservative by doing kind of the mixed partials test, you can eliminate a lot of the work involved in these triple integrals. I'm going to skip that section and just go straight to greens. So 15.4. Of course, you'll have those formulas for Green's formula. If I can find what I did with it. Test 5. Yeah, so the Green's formula, that's the first formula you see on that exam sheet there. But let's skip ahead to 15.4 then, right? So my assignments, looking at 15.4. So I'll be thinking of problems like 1 all the way up to 8, 1 to 8. And it's basically just using Green's theorem as kind of a conversion formula. Let's look at number 4. So number 4, they give us this differential form of the line integral of the vector field on this curve C. And the curve C is the boundary of the region between the graphs given by y equals 0 and y equals 1 minus x squared. So you can kind of see what that is really quick. It's y equals 0 is this. So it's this region here. We'll ultimately be integrating over because Green's theorem will convert it into a double integral. This is your m and this is your n. Those are your components in your vector field. Okay, so I need then to convert this into a double integral, so I need that formula wherever the heck I put it. That first formula there. So it's going to be a double integral of the partial of n with respect to x, which is just 1, minus the partial of m with respect to y, which 2x, and then I guess dA, whatever I decide there. Looks like I'm going to go dy and then dx. Looks like negative 1 to 1. Okay, so I got the single integral now. If I go with y first, of y minus y, well, I just write it y times 1 minus 2x, and then evaluate from 0 to 1 minus x squared dx, and then I could substitute in 1 minus x squared, 1 minus 2x dx, FOIL that thing out. So I have 1 first outer minus 2x inner minus x squared last plus 2x cubed dx. And then that will be x minus 2x squared over 2, so x squared minus x cubed over 3 plus 2x to the 4th over 4, so x to the 4th over 2, evaluated from negative 1 to 1. Plugging in 1, you get 1 minus 1/3 plus 1/2, and then minus, plugging in negative 1 minus 1 plus 1/3 plus 1/2. 1 minus 1 is 0, negative 1/3 plus 1/2, minus negative 2 is plus 2 minus 1/3 minus 1/2. Those will cancel. Negative 2/3 plus 6/3 is 4/3. Okay. And that's 15.4 stuff. 15.6, then finally we get the surface area integrals, which are also given in my formula sheet. There's the two versions now, the parametric and then kind of the z equals f of xy or g of xy they do. So be prepared for either one. So let's see kind of our question set here in 15.6. Okay, so like 1 all the way to, let's just do 1 to 6. I think that'll be satisfactory. You're just doing surface area integrals. Okay, so it's basically just a surface area integral, but with another function smooshed inside the integral, some f of xy function. Okay, so I'll try number 5. And this is the parametric form, so you're going to need the magnitude of the cross product of RU and RV. So if you remember on the form, there's, it's either going to be a normal vector, which is a gradient kind of thing, if it's z equals g of xy, or it's going to be a cross product, magnitude of cross product if it's parametric form, like in this problem. So we want to do the double integral, the surface integral of f of xy over this surface S. Our function then is y plus 4, and our surface, r of u comma v, is uv 5v. And our range of values u to 1 and then 0 v to 3. I hate the word 2 in the English language because v goes from 0 to 3 because it sounds like I'm going 0 to 3, the number 2. It drives me crazy. Anyways, I need the partials of r, and then you're going to want to parameterize f in terms of u and v so you can get the integral done. But anyways, ru is going to be 1, 0, 0. Rv is going to be 0, 1, 5. Then I need the cross product, and that'll be covering up the first column, 0, covering up the second column, negative 5, covering up the third column, 1. So then the magnitude of that thing is going to be the square root of 25 plus 1 is 26. And then you just kind of dump it all into your integral. If you want to use your formula sheet, you can. It's this, and of course you can't see my arrow, but it's that guy right there. Okay, right. So anyways, yeah. So I got this double integral of f of xy, which I want to write in terms of u and v. So y is v, then plus 4, and then I'll be going like dv, du. And then I also need that square root of 26. It's a constant, so you could just pull it out and put it in front. And then the v's are going from 0 to 3, and the u is going from 0 to 1. Okay. Sometimes you have to leave that cross product inside the integral, but in this case we got lucky. So anyways, I got square root of 26, integral v squared over 2 plus 4v from 0 to 3 du. So this will be square root of 26 of the integral of 9 halves plus 12 du. 9 halves plus 12 is 9 halves plus 24 halves, which is 33 halves, which I can factor out of the integral. And then the integral of du is just u, evaluating from 0 to 1 will just give me 1, so it should just be 33 halves root 26. Okay. 15.7 then is our divergence theorem, so changing a double integral to a triple integral of a divergence, so you don't have to integrate do a bunch of surface integrals. So it's kind of a shortcut formula. Crap, I hit the wrong button. I don't know if crap is a swear word anymore, but alright, so 15.7, divergence problems, and of course, I'm thinking of just keeping it easy, like maybe 1 to 4. Hopefully I'm not going to put anything too crazy on the test, right? So like 1 to 4 is a pretty good set. So using divergence theorem, and I'll try number 2. So divergence theorem will have a triple integral over some object of the divergence of the vector field. So the vector field they're giving us, and we're using this to find outward flux. Okay, so anyways, the vector field x squared z squared negative 6y. Is this the right problem? This doesn't look like the right problem I did. Is this the right problem? It's not. I did number. Didn't do this one. Okay, well, whatever. I'll do this one. It's not going to kill me. X squared y squared minus 6y, and then 9xyz. And of course, well, this is easy. I didn't want to do it because it was too easy. Whatever. Do it anyways. So we're basically integrating over a cube. X equals 0, x equals a, and then y equals 0, y equals a, and then z equals 0 to z equals a. So the divergence, then you need that, and that will be, it's not a vector, it's going to be variable. So it's the derivative with respect to x, so you get 2x z squared plus the derivative of the second component with respect to y, so that'd be minus 6, plus the derivative of the third component with respect to z, so that'd be 9xy. And then we want the triple integral of that divergence on this cube. So I'm going from 0 to a in each case. All right, so we won't bother writing that out. So the first integral with respect to z, I get 2x z cubed all over 3 minus 6z plus 9xy z from 0 to a dy dx. So this will be the double integral of 2x a cubed all over 3 minus 6a plus 9xya minus 0 dy dx. Okay, so do y next. So I get the single integral now of 2x a cubed y all over 3 minus 6ay plus 9xy squared a all over 2 from 0 to a, and then dx. Hopefully that is a 9 and not an a. I feel like they did that purposely because my a's look like 9s. Anyways, we have then 2xa to the fourth all over 3 minus 6a squared plus 9xa cubed all over 2 with respect to x. So this will be then 2x squared over 2. So we get x squared a to the fourth all over 3 minus 6a squared x plus 9x squared a cubed all over 4 from 0 to a again. Ugh. And then finally plugging in a, I get a to the squared times a to the fourth is a to the sixth over 3 minus 6a cubed plus 9a squared a cubed is a to the fifth all over 4. And it's easy because the setup is easy on the integral. The triple integral is pretty simple to do there. Okay. Anyways, let's look at 615.8 then, the final section. Stokes' theorem, basically changing, what is it? It's changing, where's the formula sheet? Stokes, it's changing a line integral of a vector field into a double integral over a surface. We have to remember how to do curl and where the pulleys off. Let's look at the question set. So 15.8. 15.8. Okay, so the problem's like 1 all the way up to 4 again. We'll just do 1 to 4. And I'll try number 2. Okay, so use Stokes' theorem to evaluate, and don't just put 0 for your answer. Don't do that to me, please. I know it's a 50-50 chance, but use Stokes to figure out this line integral. Given the vector field is z squared 2x y squared, and then the surface is going to be this elliptic paraboloid type object. Okay, so z equals 1 minus x squared minus y squared. You could do, your traces. So when x is 0, you get z equals 1 minus y squared, which is this. When y is 0, you get z equals 1 minus x squared, which again is this. And then when z is 0, you get a circle, x squared plus y squared equals 1. So in the xy plane, you're integrating over a circle. Okay, so I'll probably have to go polar, go the polar coordinates. What else? Not much, right? I'm going to need the curl of f. So the curl of f, to get that, it's kind of like a determinant thing, I, j, k, and then you need the partial here with respect to x, partial here with respect to y, partial here with respect to z, and we have z squared 2x y squared. So we'll end up with, covering up the first column, 2y minus 0, covering up the second column, 0 minus 2z, covering up the third column is 2 minus 0. Okay, clean that up. 2y, 2z, 2. And then finally, I needed some sort of normal vector. From this guy, the surface, you could rewrite the surface as z plus x squared plus y squared minus 1 equals 0. And so our normal vector is basically the gradient of that thing. Okay, so our normal vector is going to end up being 2x, 2y, 1, and I'm going to have to get rid of the z using that formula from the surface as well. So anyways, we'll end up with a double integral over the circle that I drew above, circle with radius 1 in the xy plane, of the curl 2y, 2z, 2 dotted with the normal vector, 2x, 2y, 1, and we're integrating, probably going to have to go to polar coordinates. So this is going to be 4xy plus 4yz plus 2 dA. And as noted, I got to get rid of that z. So this will be 4xy plus 4y times z, which is, I think, 1 minus x squared minus y squared plus 2 dA. What an annoyance, huh? So this will be 4xy plus 4y minus 4x squared y minus 4y cubed plus 2 dA. I mean, even going polar here would be a nightmare, so I'm not going to bother. I'm just going to, dy dx and go negative square root 1 minus x squared square root 1 minus x squared, because there's so much symmetry here with the powers that it's going to work out. Just trust me. Okay, and then I'm going from -1 to 1 on the y-axis, or on the x-axis. Okay. So what? If I integrate, let's see what I get. So with respect to y, I get 4xy squared over 2, so 2xy squared, plus 4y squared over 2, so 2y squared, minus 4x squared y squared over 2, so that's 2x squared y squared, minus 4y to the 4th over 4, so y to the 4th, plus 2y. Okay. Okay, so when I plug in the top thing into this big long expression and then subtract away when I plug in the bottom thing, everything will cancel out except that last term, because they all have powers of 2, and when you square a negative, it's going to become a positive, so you'll have a positive minus a positive, and they're the exact same things, so they'll all cancel out except for this part. So that's the only part I got to figure out. So it's 2 times the square root of 1 minus x squared minus 2 times negative square root of 1 minus x squared, which will be 4 of those, right? So I'll have 4 square root of 1 minus x squared dx, and then I'll be 4 times the integral of the square root of 1 minus x squared dx. That integral right there is just the area underneath semicircle, right? If you're the graph, basically that function y equals square root 1 minus x squared, you get this. And if you're integrating from -1 to 1, it's basically 1/2 the area of a circle, which is pi r squared. So I'll get 4 times 1/2 times pi times the radius, which is 1. So it's 4 times 1/2 times pi, which is, lo and behold, 2 pi. So I'll try to avoid nasty ones like that, but whew, there is a lot on the final. I'm not going to kid you. Hopefully it'll be okay. Let me know if you have any concerns. But anyways, thank you for watching. I enjoyed teaching all of you this semester from a distance, and I wish you totally the best in the future. And go on and do good things, and I'll see you later. Bye.